Okay, everybody. This is going to be our last office hours class session. So I thought we'd just continue on talking a little bit about getting variables by using the parameter read functions, and continue on a little bit with looking at the miscellaneous values and how we can pass data to the post to do things. Do want to follow up on one thing. When we left off last time, we were talking about contour flags. And contour flags are used to set some predefined variables. So I posted this single operation. And we've got M08 being turned on after the G43 line. So here's where our coolant is being turned on. And then down here, you can see that we actually had a couple different modes turned on. And we're turning off the coolant. So we're turning off flood, we're turning off whatever else we had turned on. It looks like we had 3 modes turned on. And this is coming out after the last rapid move and after the last feed move. So these 2 moves right here are part of the NCI file. These moves in here are actually called from P-Retract. And P-Retract is either called in between operations as part of P toolchange 1002, or it is called at the start of PEOF. So those are the only 2 places it's called from. If we go look at our post, so here's one of the calls, and this basically happens at P toolchange 1002 before we make the actual call to P toolchange. So what it does is it looks to see if we are processing a null tool change, which is G code equal to 1000. And if it's not G code equal to 1000, then it's part of the tool change or it's the start of file. And if it's an actual tool change, if G code equals 1002, we call P-Retract. If G code equals 1001, the else condition is true, but this is not true. So we skip the results of that, which is to call P-Retract. So at the first tool change, we do execute this code here, which is to set previous next tool. It is to set the previous home values from the home position, and we set previous feed equal to C9K. By setting the previous feed value for the first operation, we're going to force out G94. So that's what this previous feed helps us control. So when we start looking at coolant off, there's two mechanisms that control coolant, or could potentially control coolant. If I go into the machine ribbon and click on the Machine Definition Manager, our coolant options are configured here in the General Machine Parameters. So there's a Coolant Commands tab, and the type of coolant that you're using is controlled with this checkbox right here. By turning on that checkbox, that enables the older coolant settings. And the older coolant options was controlled by a predefined variable called coolant $. But it has some limitations. The first limitation is that you only get 3 coolant options. You can see that the rest of the options below 3 are disabled. And the other limitation is that you can only have a single off code. So those are the kind of limits to the version 9 coolant. For most people, I recommend that they disable support coolant using coolant value in the post, because this enables you to use 10 different coolant options and to have a separate on-off code. By the way, there is first coolant off command shuts off all coolant options. There's this extra checkbox here, so you need to be aware. If that's checked, it's only going to use this first off command, which is typically M09. So turn off both of those checkboxes, and you now get up to 10 different coolant options with separate on-off codes. The only thing that is tricky about using the X style coolant is to know where are we grabbing values from. If we go look at the generic Fanuc 4X mil post. Oh, I overwrote this one apparently. Okay. Well, let's go. There we go. We'll go back to an older version of the generic Fanuc 4X mil post. When we make edits to the X style coolant using a CNC software post, we actually have to go down and edit the string select table. So there is a string select table that is available for us, which has 20 values. It's coolant codes 1 through 10, and each of these strings is an on value followed by an off value. So you can see here, SCool50 is M8, SCool51 is M9, coolant value 2, SCool52 is M7, SCool53 is M9. Okay, and so on. So we actually have to go into this string select table and make our edits. In MP Master, there is some code that they added to go and make your life easier for you. Scroll down through all this stuff. Type. This is all the calculation type stuff. And eventually we get down to the tool table. So here we've got PWRTT, P tool table. And let's go find, I think it's actually P set machine. Here it is. Okay. So in P-Sync lathe, which is the predefined post block that gets called for the NCIG code 950 line, we call P-Set Machine. P-Set Machine sets some variables to 0, and then it makes a call to the control definition parameters. So it reads all of the CD parameters and sets all those parameter values. Then we have a little bit of logic. And that little bit of logic says if SOF equals 1, execute this code in here. Now, I've added some extra stuff down here, but typically we set read machine ent no, which is a helper variable, to 0, and then we call rdmd. When we call read machine rdmd, Mastercam, or should say MP, repeatedly makes calls to p machine info for all of the parameters that fit in the range for the machine definition. So p machine info is down here, and this is the code. This line right here, 1746, is what calls or sets all of the machine definition information. So if the parameter code is greater than 17,000 and it's less than 18,000, the result is that we run parameter table number 1. And parameter table number 1 is here. And it grabs potentially 42 different variables. And what you'll see here is that they've added the code to read the text strings directly from the machine definition general machine parameters interface. So rather than forcing you to edit both the general machine parameters and the string select table, they capture it for you here. And if we search for scool50, you can see that we have the same string select table. However, all of the default string values for the X-style coolant are just empty strings. And this is what allows us to build the structure of the string select table, which is right here. So all the strings and then F, str, sel, scool50, coolant X, scoolant X. So this is the start of the list of strings. This is the variable that actually controls which string we select from the list. And this is the variable that outputs that value. Okay, so MP master fills in this table for us. If you're using the generic Fanuc posts from CNC software, you have to either add these to the machine definition parameter table, the way that In-House Solutions has done, or you need to edit the string select table independently of the general machine parameters. So really there's two different ways to approach it. Now, when we're using X style coolant, you'll search for Retract. So you can see here with Retract, we call PHSM off, which shuts off the high speed if it was turned on. These 4 lines here are saving the current values of AbsInc and the current value of coolant $. And then we force AbsInc to 1 and we force coolant $, to 0. And what this does for us, these coolant $, and AbsInc are used as selector variables for a string select function. So when we see that target variable on the output line, the current value of AbsInc is going to be different from the previous value of AbsInc, and therefore we're going to get output. So down here, when we hit SG AbsInc, this is where we're going to get our G91 to come out from. And the thing that controls it is actually right here. So setting AbsInc to 1 means that we have changed the modality, and this will now output. This mechanism right here, and you'll notice it says uncomment this line to leave coolant on until end of file, unless explicitly turned off through a can text edit. So you can have it where you turn coolant on at the very beginning and all the other coolant codes are ignored until the very end of your program. And by uncommenting these lines here and this line here, we can tell it leave coolant on no matter what until the end of file. What we've got here with this chunk of code is a mechanism for turning off the coolant. The first test, if all cool off. Okay, this predefined variable is actually read from this checkbox. So if that checkbox is turned on in your machine definition, this variable will be set to yes or 1. There's some other code that does that. If this is turned off, then that variable will not be true. And if it's not true, we skip this code here and we move on to the else statement. So the else statement is a loop. This is what's known as a while loop. And what we do is we set local int to 0. So we're setting the value of this variable to 0. And we're setting coolant x equal to 0. And then we start the loop. So the way that this loop functions, it first evaluates local int. Well, the first time that we evaluate it, what is the value going to be? The value is going to be 0 because we just set it to 0 right before we entered the while loop. So this will be 0. It is less than 20. Therefore, we're going to execute all the code in here. And the first thing that happens is we set the value of coolant x, but we do it in kind of a sneaky way. We do it by using what is known as a bitwise math operator. So this is kind of a funky deal. It says return equals A and D, and in parentheses it has 2 parameters. It has the integer I and the integer j. Really, those are just representing parameter number 1 and parameter number 2. So with the AND function, it returns a binary integer if both bits are 1. Then the corresponding bit in the return value is 1. Otherwise, if they are both not 1, then it returns 0. And you can see here that it uses 2 to the power of the local integer. And it is comparing that to coolant on. Now, coolant on is a funny variable. What you have to understand is that coolant on did not get set here. Actually, I'll do that. So coolant on was already set before we entered this post block. And coolant on contains the sum of all of the different coolant options that have been enabled. And we do that with a really interesting data structure. So I'm going to search for coolant on. Okay, so this p_can_text_out post block is where the coolant output strings get built. So this is the code for determining is coolant on and what should its value be. Coolant bin, we do a search for that. So the key here is coolant bin gets set by this lookup table, and it's lookup table number 2. So it's FLK TBL. And this lookup table here is what defines what is turned on and what is turned off. So it uses the can text value 50, 51, 52, 53, 54 to determine the integer that we are going to add to this coolant bin number. So if you look at coolant off for number 10, that would return 524288. If coolant value number 10 is on, it returns half of that number. It returns 262144. Then if coolant value 9 is off, we add this number. If it's on, we add that number instead. So what we're doing is we are adding up the sum of all of the on-off values. And that's going to give us a unique integer value that then gets compared to this logic. So this is where we take the can text value, we do this flook function for lookup table number 2, and we set the value for coolant bin. And then what we do is we take the can text value and we divide it by 2. If it's an odd value, the frac command looks to see if there is a decimal portion on the number. So when we divide an even number, there's no decimal portion. When we divide an odd number, this is true. And if this is true, then it goes in and it runs this code here. So if it's off, if all cool off, it's going to run this. Else, coolant on equals coolant on minus coolant bin divided by 2. So this coolant on maintains the current sum of all of the on-off values. And we have some more while loop logic down here to determine if we're going to output or not. So if the coolant code's already on, we don't output a value that's already turned on. So in P-Retract, this code here is what looks to see if our coolant is on and then turns it off. So if we're using the version 9 style coolant, it's a lot more straightforward. It's a lot easier to tell when something has been turned on and when something has been turned off, because it's given to us with this flag variable coolant $. With X style coolant, we have a variable that maintains the integer sum of all of the coolant on-off values. So it's a little bit harder to move around turning coolant off if that's what we want to do. But we can do it. So here we're in P-Retract. You can see that this is the older coolant stuff. This here is the newer coolant stuff. And S coolant over here is used with the older coolant stuff, with the version 9 stuff. So here's what we're going to do. This is kind of the P-Retract coolant off code. So okay, P-Retract cool. I'm going to create a new post block. Shut off X style coolant at P-Retract. What I'm going to do is I'm going to paste all that stuff in. This is again P-Retract cool. And then inside P-Retract, I'm going to call P-Retract cool. so this code, you can see here, checks coolant on, and at the very end of running this while loop, coolant on is set to 0. So that's what I'm going to use as my flag for this. So we're going to say if coolant on, in other words, if this value is not 0, we're going to call p-retract cool. That way we don't end up calling this if coolant on is already set to 0. So what we've done is to maintain the exact functionality that was there. The reason I'm doing that, I'll show you in just a sec. So I just reposted, we have the same PHSM off right here, and we get our same coolant off codes right here. And I get requests pretty often of how can we move my coolant off code to the retract line. And that's what we're going to look at, how can we do that. So let's go ignore on that. And the weight is on so we're just going to use flood. Not that we can't use all of them, but I think it'll be easier to track if we just do this one at a time. So we should be getting an M08 at the tool change. M08, M09, you can see it's after the retract move. Then we have a tool change to this tool here, and we have our M08. Now, because we had a null tool change, and operation number 2 uses M08, and operation number 3 uses M08, you can see that there is no change in between these two operations. There's already logic in there to handle that for us. But then down here, we do get our M08 after that retract. So what we want to do is see if we can flag the motion inside MP master. And we're going to search for P rapid out, P lin out, and P sur out. Typically, it's either going to be P lin out or P rapid out that is going to output our last move. And that's all based on the order in the NCI and how we have set up lead in and lead out. So if I look at my contour here, I've got my lead in motion, I'm rapiding down to a feed plane, I'm feeding the rest of the way, I'm doing a linear move that is tangent to the end of my arc, I am arcing in, and then I'm doing my cut motion. So this is all cut motion. All that we know inside the post is that we're in the middle of a cut. And then we'll do our exit motion. So here is my exit arc. Here's my exit line. Here's my exit linear retract. Here's my exit rapid retract back to the clearance plane. And what we'll do in the post is we're going to look for contour flags or variables that we can use to test and see where we're at in the motion. Let's do a variable up at the top. Okay, so I'll create a new variable, force debug underscore m. I'm going to use this for debugging the motion. Okay, so in P rapid out, before the start of the output, okay, we're going to say this is debug motion output. What I'm going to use for output is the tilde character. And the tilde, which looks like a little sine wave, just below the escape key or just above the tab key, is used for debugging. What it does is to allow output of the variable without changing the current value and without updating the variable. So it allows you to output it without disturbing any of modality or any other mechanism that may be active. So I'm looking through. Looking through the variables here. C flag. Well, I'll tell you how we can look it up. We go back to the documentation. If we go to the NCIG codes, CUR underscore CFLG. So the control flags, this is the variable that's output from the NCI. And it is used to set the start and end of contour information, contour stop information, optional stop, and it's supposed to also hold coolant values, but I never rely on it for that. So the control flag, also called contour flag, parameter is a single parameter passed from the NCI that carries several pieces of information in a single numeric value. The control flag parameters appear in every NCI motion line, G code 0, 1, 2, 3, 11, and 81, to control such values as contour stop, contour start, contour end, coolant, 5-axis angles, or rapid behavior for lathe. what the C flag boils down to is that it's a combination variable. It's up to a 6-digit number, so it can have as many as 6 digits or as few as 1 digit. And each value is kind of, they call this a license plate scheme. So each place, this is the ones place, this is the tens place, this is the hundreds place, thousands place, 10,000s, and 100,000s place, right? So this is a 6-digit number here. Each place is used to set another predefined variable. C stop, CG stop, C end, C start, rapid type for tool inspection, and coolant. But again, this doesn't play well with the newer X-style coolant, unfortunately. Now, we have to be aware that for this to work right, that we have to disable this. So if rote on X equals 0, cut pause 2 equals M1. If that is turned on, then it's going to disable cut pause 2. We don't want that. So I'm going to make sure to disable that line of code or even remove it. So I can always cut that line out if I wish. So oh, come on, I wish that would move out of the way. So I can move it down here without getting anything in the way. Okay. So cur underscore C flag is the variable that will hold our potentially up to 6-digit integer that kind of tells us where we're at within the cutting. Derived from that variable is C start, C stop, CG stop, and C end. So all of these other variables get set from current C flag. So what we'll do is we're going to debug current C flag. We're going to debug cut pause 2. Now cut position is only used for 5-axis. Cut pause 2 is the universal toolpath flag, which is used on all toolpaths. So we want cut pause 2. We also want C end. Oh, that's CC end. We don't want CC end. So CC end would tell us cutter comp. So we've got CC end and CC start for cutter comp. We have C end as the end of contour flag. So it's important to get the right one. Now, C start and C stop, or C stop and CG stop for the MO1 stuff isn't really as important as seeing the current C flag, cut pause 2, C end, C start. But then there's also a tricky one. next C flag. So when we are running normal NCI G code, so normal post-processing, Mastercam MP is reading 2 lines at a time from the NCI file. We don't really know what's coming ahead of where we're currently processing. So what CNC software built was a mechanism in the post called getNextOp. getNextOp runs during the pre-read routine, and it records values. It records the current value 1 position behind, so that we can get a peek 1 line ahead to know what's coming next in the NCI. So it's very important that this getNextOp variable is turned on in order for next C flag to actually get set. So I'm going to add this force debug to both PRapidOut and PLinOut. And if we post the same 3 operations, let me make sure I save that. And now you can actually see here, this is our Z10 rapid move. And if we look, let's look actually up here. So this is GO2, GO3. So here we're exiting, and current C flag is 200. Cut pause 2 equals 4. C end equals 2. C start equals 0. Next C flag equals 0. And what you can actually see here at the end of, actually let's just take this whole operation. So here's where the operation starts. We have a tool change. And then we come down here for our first rapid move. You can tell it's rapid because it just says Z.2. So we were in GO mode. There's no GO1 present, so we know we're in rapid, but it also shows us debug rapid. Current C flag 0. Cut pause 0. So you see this next C flag, everything is just 0. Then we go to this rapid motion right here. So what actually happened is that we had 2 rapid moves in a row. So you can see debug rapid and then debug rapid right here. Next C flag is 2000, but there was no output. If we wanted to do something, we could do something here by reading next C flag, and then based on, if next C flag equals 2000, do something. So if we wanted to have output between the first linear move and the starting rapid move, we can do that here. Oh, but you know what else we need to do? Sorry guys, I messed up. I've got PLinOut. But I had rapid there. So that's what was going on. Let's try that again. Okay. There we go. So this is the rapid move. This is our first line. And what you can see is that on the first line here, where we're actually just feeding down in Z, we have not started the contour cut, because this is our, remember, this is still technically a linear feed move down. We're not starting the contour. But what you can see here is that next C flag is 2000. So when we go to our next move, this is our G41 move. This is the line on which our cutter comp is being turned on. Current C flag is 2000. Cut pause 2 is 0. C end is 0. C start is 2. So if we were to use the C start variable and test for the condition 2, we can tell if we are on this linear entry move. If we look at the next line, GO3, so that's not really going to do much for us, right? This is the entry arc. If we happen to put some debugging on that, we could let's do this as well. So we're going to do force motion debug, and before psir out, we're going to debug the arc. Okay, so we'll post these three out. And you can see, so here's our G41 line. Let's do this. Let's help we're going to force a blank line before each of these debug lines, just to help break us up a little bit, help isolate everything. Okay, so we start with our very first rapid move. We plunge down with our first line. Next C flag's 2000. This is our entry move, G41. Current C flag 2000. Cut pause 2 is 0. C end is 0. C start is 2. On this arc, you notice cut pause 2 is 1. So we've started our entry motion, and this is still the lead in because cut pause 2 is equal to 1. Now we've finished our lead in move. So you notice right here, current C flag 1000, cut pause 2 equals 2. C start is 1. So this is where the contour really starts. C start 2 means that we're on the entry motion. C start 1 means this is the first move of the contour. And then you'll notice as we go down here, cut pause 2 is equal to 2. Cut pause 2 is equal to 2. Cut pause 2 is equal to 2. This is true as we go down throughout the operation. You'll notice that C end, C start, next C flag, and current C flag all say 0. So cut pause 2 equal to 2 means that we're in the cut. All of this is in the cut. And then we have the last line of the contour. Now I can tell it's the last line of the contour only because next C flag equals 100. So even though all I've got here is a Y0 move, I could test next C flag to tell me, okay, I'm at the end of the contour. Now here's where we really know we're at the end of the contour. Okay, Debug Arc, this is the last move of the contour. So it's actually where we're coming around this corner here before we make the exit move. It's that corner right there. So this Y0 motion is actually the next to last move. The last move is this arc. And the arc shows us current C flag 100, cut pause 2 equals 3. In other words, when cut pause 2 is equal to 3, or when C end equals 1, we're in the last move of the contour. So this is literally the last move of the contour. Then we have cut pause 2 equal to 4. Okay, current C flag 0, C end is 0, C start is 0, but this is the lead out arc motion. Then we have cut pause 2 equals 4 and C end equals 2. Okay, so this is telling us this is the last move of the contour. Then we have a move where cut pause 2 is equal to 4. And here cut pause 2 is also equal to 4. So what we can do then, you notice C end is set to 2 here and it's set to 1 here. So this is basically the last several moves of the contour and the lead out motion. And if we go back up to the top, so Cn 0, Cn 0, it's always going to be 0 until we get down to the end. Now, part of what complicates this a little bit is that we don't know how every programmer is going to program. And that's a big deal. Because what happens if they do this? What happens if they go into Contour 2D and they turn off lead in and lead out? That means all the numbers that we were getting from the contour flags are going to change. So it's not necessarily as cut and dried as just, oh, test C end and you'll be good. So here we are getting some line motion to end the contour, which is interesting. Oh no, this is the last op. So here, C end is equal to 3. So it really depends on how you've got your lead in and lead out set up. But we still should be able to capture if we're at the end or not. So let's do something. We're going to write some code to move the coolant off output ahead 1 or 2 lines. Before we do that, we're coming up kind of on the midpoint of class. Let's go ahead and take our mid-class break. We'll come back in about 15 minutes, and then we'll look at how do we test cut pause 2 and C ends and the C flag stuff to be able to move output around. Okay.